A modified CNN for detection of faults during power swing in transmission lines. The integrity and protection of transmission lines is very important for a power system grid, and hence timely isolation and clearance of faults in these lines is very crucial. For this, we have various traditional protection schemes integrated with the existing power systems. And the most basic component in all of these schemes are relays. Relays are set to trip during any abnormal condition in any of the three phases of the power lines. But in cases such as power swing, there might be sudden surges in voltage or power, but it stabilizes on its own. And here, relay action is not necessary. If the relay acts, it might cause unwanted oscillations, and so we have the power swing blocking mode in a relay. But there are cases when a three-phase fault or any fault, for instance, happens along with the power swing condition. Here, if the relay remains to be ineffective, there can be serious consequences such as abrupt imbalances in power, and this might even result in blackouts. Our objective is to model a power system grid and create an efficient algorithm to accurately differentiate fault conditions, power swing cases, and those cases where fault as well as power swing occur together, and in turn ensure proper relay operation, hence overriding the power swing blocking mode of the relay. For this, we have created or simulated a three-phase system, that is a three machine 9 bus system and an infinite bus system. This was simulated by applying a fault in a certain phase at a set time and clearing it after a fault interval. The waveforms were recorded, sampled, and collected as time series data. This is in accordance with the swing equation of the generator describing relative motion between the rotor axis and synchronously rotating stator field with respect to time. Waveforms for real power, reactive power, load angle, current, and voltage for the three phases were recorded. The system is simulated to identify normal case, line to ground faults, double line to ground faults, double line faults, triple line faults, and three phase to ground faults as well. And all these cases for all the three phases and even the normal case together. And hence, we have a total of 24 cases that have been simulated. This data that has been recorded or this one-dimensional data that has been collected is given to a modified one-dimensional CNN algorithm where features are extracted and mapped to encode labels. It fundamentally consists of 5 definite layers. The 1D CNN layer has 64 filters, 3 batch normalization, and max pooling layers with strides of 2 and pool size of 3 to downsample and reduce the size of the feature map. The flattened layer converts the multidimensional array into a single vector. The dense layer wraps it all up into a fully connected layer, interconnecting the neurons from the input layer to the final output layer with ReLU and softmax activation functions. The model uses Adam Optimizer with a categorical cross entropy loss, and we run it for almost 30 epochs. The same time series data is processed in an LSTM model with 256 memory units and a dense as well as a sigmoid activation layer. It has an Atom optimizer, and the same data is again used with other machine learning networks such as decision tree, KNN, naive Bayes, etc., to classify, process, and make predictions. Feature scaling and standardization of the data is done, and the data almost consists almost from 5,000 to 10,000 samples. This is divided into training and testing data in the ratio 70 is to 30. Accuracy, precision, and F scores are used as measurement performance measures to analyze the different models. This slide shows the details of the data sampling standardizing of our proposed CNN layer or model. These are the results for various machine learning techniques that have been used, And we have KNN with almost 87.9% accuracy, the decision tree with 94.5% accuracy, and the naive Bayes that resulted in 94% accuracy. So we have the highest accuracy for decision tree in machine learning techniques. The deep learning techniques, LSTM and modified one-dimensional CNN, for different number of samples were collected, and we have arrived at the conclusion that modified 1D CNN tops it all with with almost 99% accuracy. This is a graphical representation of our work, which shows the results from various techniques that have been used in the WSSC 9-bus system and the infinite bus system. Our proposed model showed the best results in identifying faults, power swing, and critical cases of faults that have occurred with power swing, and hence has found most apt for real-time applications. The sensitive and F score of the infinite bus systems are 99 and 99.6%. This is also really good. The reduced complexity, easier training, and possibly simple integration with the existing power system, which is consists of a lot of digital relays, make it a more feasible solution. This work can now also be extended to be implemented or simulated on a more practical system like the EHV grid of a complete state such as that of Kerala, and this can be considered as a future scope of our work. These are our references, and thank you.